In this section, we are going to study how to solve the homogeneous linear systems. In the last sections, I introduced the general form of the linear systems. dt x equal ax plus f. In the case of the homogeneous differential equations, this f equals 0. So in the case of the f equals 0, this is homogeneous linear systems. And the x is a vector quantities and the A is a matrix. Then we'd like to find out the solution of the x. So solution of the x is expressed with the vector quantities and the non-zero vector of the k times exponential lambda t's. So this vector quantities are using the capital K times the exponential lambda. Then we'd like to substitute this form of the x into the differential equations. So x prime is a derivative of x with respect to t, and the k is a constant quantities. We don't have to consider the derivative of k with respect to t. So k constant vector, and the derivative of the exponential functions becomes a lambda exponential lambda t. So k times exponential lambda t is equal to the x. So x prime is equal to the lambda x. Then actually you can substitute this equation into the original differential equations. So x prime equal ax. X prime is lambda x equal ax. So from this equations you can find that a minus lambda I is a unit matrix, times k. So unit matrix is in the case of the 2 by 2 matrix 1 0 0 1, or 3 by 3 1 0 0 0 1 0 0 0 1. These are unit matrix I. We could write the a minus lambda I times k equals 0. From these equations, if a minus lambda I inverse of the matrix exists, then by multiplying the inverse of the a minus lambda I, we could find that k becomes 0. But k equals 0 means actually this is equal to the x equals 0. So we are not interested in the x equals 0. Of course, this should be the solutions of the given differential equations, homogeneous linear systems. But we are not interested in such trivial solutions. Therefore, in order to non-zero k, a minus lambda I inverse of this matrix does not exist. So this means determinant of the a minus lambda I need to be 0. So this is the equation to determine the lambda. And we call the lambda is eigenvalues. Eigenvalues and eigenvectors. As I explained, we have a characteristic equation is a determinant a minus lambda I equals 0. By solving this characteristic equation, we could find lambdas. Once we find the lambdas, we need to find the corresponding eigenvectors. Corresponding eigenvectors, actually we can substitute the lambdas. This eigenvalue is a lambda into the original equations. Then find the corresponding eigenvector k. So by solving these equations. So this is a method how to determine the eigenvalue and the eigenvectors. So I'd like to show you the example. So find the eigenvalues and the eigenvector of this matrix of A. 1, 2, 4, minus 1. The first thing to do is solve the characteristic equations. So determinant a minus lambda I is equal to the, sometimes we could use the same symbol for the absolute quantities a minus lambda I. Then a is 1, 2, 4, minus 1. So 1 minus lambda, 2, 4, minus 1 minus lambda. So this is equal to the 1 minus lambda. minus 1 minus lambda, minus 2 times 4. So this is equal to the lambda square minus 9. So characteristic equation, this is equal to the 0. From this equation, we could determine the lambda. Lambda equal plus minus 3. In the second step, we need to find the corresponding eigenvectors. For lambda equals 3, you can substitute lambda equals 3 into these equations. Then it becomes a minus 2, 2, 4, minus 4 times the vector k sub 1 equals 0. So to satisfy this equation, you can choose a k sub 1 equal 1 ones. Also, you could choose a 2 twos or 3 threes. It's a multiple of the 1 1 vectors quantities. So in this case, we choose the most simple case of the 1 ones as an example. So this is a eigenvector corresponding to the eigenvalue of the lambda sub 1 equals 3. So we could do the same type of the calculation in the case of the lambda sub 2 equal minus 3. Substitute into this equation, it becomes 4, 2. 4, 2 times k sub 2 equals 0. So to satisfy these equations, we choose k sub 2 is 1 minus 2. Okay, so I explained how to find the eigenvalues and the corresponding eigenvectors. Then find the characteristic equations possesses n distinct eigenvalues. This is a case of the distinct eigenvalues. Lambda sub 1, lambda sub 2, up to the lambda sub n. All eigenvalues are different eigenvalues we have. We find the n corresponding eigenvectors k sub 1, k sub 2, up to the k sub n. Then solutions of the differential equations. Homogeneous differential equation is given by c sub 1 times k sub 1 times the exponential lambda 1t. So this corresponds to x sub 1. And the c sub 2 times the x sub 2 up to the x sub n. So by summing up the n terms, we could create a general solutions of the differential equations. So I'd like to show you the example. Solve the homogeneous equation. Then as I explained, this corresponds to the A. Then find the eigenvalues and the corresponding eigenvectors. As I explained, we discovered that lambda sub 1 equals 3. The corresponding eigenvector is 1 1. And the other eigenvalue is a minus 3. Corresponding eigenvectors is a 1 minus 2. So from this one solutions is expressed k sub 1 times exponential lambda sub 1t. Also from the second pairs, we could create a x sub 2 and k sub 2 exponential lambda sub 2t. By multiplying the two parameters, we could create a general solutions. So this corresponds to x sub 1s and the x sub 2s. I explained how to solve the homogeneous linear systems. At first, we need to solve the characteristic equations to find the eigenvalues. Once we find the eigenvalues, we need to find the corresponding eigenvectors. Once we discovered eigenvalues and eigenvectors, we build general solutions of a system of equations. Okay, this is the end of this session.